Okay, that was extremely jarring. Is everyone still there? Okay, I don't know. That was very weird. Okay, yes, that freaked me out also. I don't know if you saw me jump. Um, yeah, I guess they really want us to know that the meeting is being recorded. Okay, so anyway, it's the exact same syntax as all the other classifiers we've seen. Um, and you can set the number of neighbors. Great question in the chat. Does it not consider any weight on the distances? So this is another hyperparameter you can put in. So weights equals uniform means that it just finds the k nearest neighbors, be it 5 or 100, and then does a vote. But there's a weights hyperparameter that has two options in scikit-learn, or you can kind of pass in your own custom thing. The default is uniform. The other kind of built-in one you can choose from is distance. That basically means instead of doing an equal vote, it does an unequal vote where closer neighbors have more of an influence than farther neighbors, which kind of makes sense. And I'll show you more examples of that in a minute. Okay, so yeah, you can call .score on this, and it's all just the usual stuff. And so k is, like usual, a complexity hyperparameter. And generally speaking, smaller k is more complexity, which is not super obvious why using a smaller number of neighbors makes the model more complex, but let me show you the picture. So when you set k equal to 1, your prediction at any given point just looks at the nearest thing. And so if you have a single, say, red thing over here, it'll immediately switch to red around there. So k equals 1 means it only takes one training example to change how you predict in that region. And that could cause overfitting, because what does overfitting mean? Well, it means you're too sensitive to the peculiarities of your training set. And so if it only takes one example to completely change your prediction in a given region, then that could be overfitting, because maybe you need to see more examples. Maybe you need to see 5 examples of something to be convinced there's actually something going on now. And so then you could set k to be 5 neighbors, and then you would get these less kind of jumpy decision boundaries. So here we get, well, here we get 100% training error, which goes to the idea of what someone posted earlier, that when k equals 1, if you're trying to predict a training example, its nearest neighbor will be itself. And in this case, we also get a better test error. Yeah, so I should say, I don't think we actually talked about RBF SVM, so I think we can just delete this out. But there's something else called an SVM in scikit-learn that's very similar to this k nearest neighbor. I took it out this time around though, so I'll just delete that comment. Any questions about all this? Okay, so is there any reason why you're avoiding SVM? Not particularly. It's just one of many possible models you might use in machine learning. There's no particular reason why I'm avoiding it. And you can use it in scikit-learn. It's called SVC and SVR in scikit-learn. I just feel like I didn't want to clog the course with tons and tons of different models, and that's not really what the course was about. And the kind of like the kind of defaults I'm giving you in this course is like dummy, regressor, or classifier, and then maybe try a linear model like linear regression or logistic regression, and then maybe try one of those tree things. But yeah, in reality, you might try a whole bunch of stuff, including SVMs. I just feel like on a randomly chosen problem, it's less likely to be the best choice than the things that I'm focusing on. Any other questions? Okay, so let's talk about regression. So as we've seen for most of the things in the course, there's like the regression and the classification versions, like random forest classifier, random forest regressor, etc. So with k nearest neighbors, there's the regressor version, and I'll just show you what it looks like. So here, this is just, again, these are not real data sets, just for illustrative purposes. So here's a case with just one feature, and here's the target, and the red are the training examples, and the blue line is the predictions. And basically what it's doing is, if you want to predict at a particular place, it's saying, well, what is the closest training example since k is 1 here? What is the closest training example? And I'm just going to predict that. And so what it means is your kind of prediction surface is basically flat, as long as, where is my pen? So for example, over here, it's computing distance in this feature space. So if your prediction is over here and the nearest neighbor is this training example, then it's going to predict the same y. And if you move around a little bit, if that stays your nearest neighbor, then your prediction is just going to be whatever that value was. And so if you move around a little bit, your prediction is not going to move at all. But if you move too much and you want to make a prediction over here, then the nearest neighbor changes. Now a different training example becomes your nearest neighbor, and so your prediction jumps down like this to the value associated with that other training example. And these are just like, yeah, 2 feature and 1 feature examples, because those are easy to draw. But just like any of the methods we learned, this will work with any number of features. You could do this on the housing data set, the fraud data set, all the data sets we've looked at. You can do k nearest neighbors on, and you can get the score, and you can change number of neighbors to 10. And so what happens here is it's looking at the 10 closest neighbors. And so again, you can feel like it's kind of overfitting less in that it's not going to completely change the prediction just based on one training example. It's kind of a more smoothed out trend, because as you move over, your prediction is the average of the y value for the 10 nearest neighbors. And so with the houses cases, you would find the 10 houses most similar to your house, average their prices, and that would be your prediction for the price. Yeah, so going back to this weights thing that someone asked about earlier, you don't have to take an actual average. You could take the 10 houses that are most similar and say, but the house that's really, really, really similar, I'm going to put more weight on that when I'm averaging the prices. And the house that is only kind of similar, I'm going to put a bit less weight on that. I'm going to do a weighted average of the 10 most similar houses. And that's completely fine. And the picture of that, well, it looks kind of funky. And it depends exactly how you implement the weights. They've implemented it in a certain way in scikit-learn, but you get these kind of more curvy looking surfaces instead of these step functions here. Okay, so yeah, KNN is another approach that you can use. It can be used for classification or regression. Works by finding the k nearest neighbors to a query point. Choice of, and so this relies on a choice of distance, because again, it's, well, all the stuff we talked about last time, which things are going to be your neighbors depends on which distance metric you decide to use. And so just like with the scikit-learn nearest neighbors, which we used last time to find similar items, or this k nearest neighbors for supervised learning, k neighbors classifier or regressor, you can also use different distances. It uses Euclidean distance by default. So why would we want to use this? I mean, it's kind of like, this is one of the cases where you can fully understand how it works. You could probably implement it from scratch. And so it's more understandable than some of the stuff like XGBoost, which is more opaque in terms of how it is all working under the hood. We have a let's all these typos today. We have a simple hyperparameter, and it can learn very complex functions. So if you have lots of data, if you set k small enough, you're not really going to underfit with k nearest neighbors. A huge con for this is it can be extremely slow, and in particular, whenever you make a prediction, you kind of need to refer back to the whole training set. And so almost all of the things we see in this course, basically everything else we see in this course, fit is the part that's slow and predict is super fast, because fit needs to do all the learning from the data. And then once you've got your trained model, you can kind of predict pretty easily. In this case, fit hardly even really. In this case, when you predict, there's still a decent amount of work that needs to be done. And if you're literally just looking through all the neighbors to see which one's the closest, that's going to be super slow. It uses some fancier algorithms in there. So if you've taken algorithms course, you maybe heard of something like KD trees. It does some fancier things, but at the end of the day, it's still very slow. And yeah, again, just based on my feeling is on a randomly chosen problem that you might be working on in the future, I would first try a baseline, I would next try a linear model, I would next try some sort of tree-based model, and then you might start thinking about other things as well if needed. Yeah, and just a note here that you should definitely scale your features. Well, in this class, we're just always scaling our features, so it's not even really necessary to say that. Any questions? Okay. Yeah, okay. I have a feeling this is better for smaller data sets. Yeah, I mean, I think that's fair just because it's so slow. You might find it too slow for huge data sets, even with some of these fancy algorithms. Is there some best practice using KNN, when to use KNN? I mean, my kind of general answer in this course is do whatever works. You know, when you're working on a problem, try a bunch of things. If you have the skills to do your cross-validation in a kind of safe, trustworthy way, then you can do a bunch of experiments to compare different approaches, and you can decide what's best. And you might take into account all kinds of factors, including speed, not just cross-validation accuracy. The only other thing I'll add is there's certain unusual cases where it's hard for you to describe your training examples as like vectors of numbers, and it's easier for you to describe distances. So just as an example, maybe you're like trying to classify different types of music by their genre, and maybe you don't really know how to turn in a piece of music into a bunch of numbers, and so you don't know how to feed it into random forest or something like that. But maybe you have a piece of code that takes two pieces of music and tells you how similar they are. Well, that's actually all you need to run KNN. You don't actually need to know a vector of numbers for each training example. If you just have the ability to compute the distance between them, even without knowing what they are, you can already use this. And so there's certain cases where that's a big advantage, and it's rare, but it's good to know about that you may find yourself in a situation like that. And there's certain methods like this KNN, like the SVM that I mentioned, that you can still do machine learning even without being able to turn your examples into a bunch of numbers. Just out of curiosity, is there any Bayesian approach going on under the hood? I'm super unfamiliar with the algorithm. There's no Bayesian approach going on under the hood in anything that we talk about in this course. I think except early on in the course, we talked about hyperparameter optimization. I had like an optional extra video about Bayesian hyperparameter optimization. I don't think anything else in the course is. Okay, so I have this true or false thing, but I see, just looking at the time, I'm going to leave this for now, and if we have 10 minutes at the end, we can do this. That should say 100. And if we don't have time in the end, I'll just put these on Piazza as usual. Okay, so that was sort of the finishing up the stuff from last time. And now I'm going to talk about natural language processing, which is what I'm going to talk about for most of the rest of today. And yeah, I'll still wait even longer to address that question about feature engineering. I'll wait until the end. So as I mentioned, the second half of the course that we're in now is a bit different from the first half of the course in that I'm talking about kind of common special cases of different types of data. So I talked about images, and on Thursday, we're going to talk about time series data. And so today I want to focus a little more on text data because text data is super common. And it's true that we've already seen text data in the course, but we've only used count vectorizer. So today I'm just going to broaden things a little beyond count vectorizer, and that'll be kind of the goal. So NLP is an acronym for natural language processing. It basically means doing stuff with language data. And just like a week ago when we talked about computer vision, I said there's a whole bunch of tasks like what is in the image, where are things in the image, dividing the image into pieces. There's also many tasks you might be interested in when it comes to language, like translating languages, summarizing text, sentiment analysis, which we kind of did, like is this positive or negative review, relationship extraction, chatbots, all these kind of things. So this is a massive, massive field. And we'll only talk about a tiny bit today, but hopefully it's better than nothing. Yeah, this relationship extraction one is actually very interesting. One of the Master of Data Science capstone projects a year or two ago was that the students were trying to extract relationships between public companies based on public filings. And so all these public companies have to file documents, and then they talk about other companies in those documents. And then they try to automatically mine all those things and build like a social network of like this company is kind of collaborative with that company, but competitive with the other company, all being automatically extracted. I thought that was really cool. Okay, so I'll just start with a couple examples of why language data is so hard. So first one is Panini. So yeah, I mean, Panini was a person, but it's also a type of sandwich. And so if you see the word panini in a document, there's this ambiguity of, well, what are they talking about? There's part of speech ambiguity. So fruit flies like a banana. Okay, so does that mean fruit flies like the noun, or does that mean fruit flies like a banana? Well, we kind of know it's probably the first because fruit doesn't fly, but I mean, you never know for sure. So again, this makes it very challenging. Yeah, right. Okay. If the baby does not thrive on raw milk, boil it. So I guess, again, we can be pretty sure that it refers to the milk here and not the baby. But if you're just a computer and you're ingesting language data, there's just so much ambiguity that's kind of obvious to us. It just sees it. And so all I'm really trying to say here is doing stuff with language data is very hard. And so, yeah, I don't want you to leave the next hour feeling like you're an expert in, I mean, maybe you are already for other reasons, but I'm certainly not an expert in this, and we can't really cover this whole thing so quickly. Okay, yes, you could do an entire degree on NLP. Actually, we have this computational linguistics branch of our Master of Data Science program. That's this link here. yeah, in this class we'll mostly talk about turning text into numeric features. So let's load back this movie review data from lecture 4, where we used count vectorizer. So to remind you, we had these movie reviews and we were trying to predict the sentiment, if it was positive or negative. So here's one of the reviews. And so what we did so far, I'm going to keep going a little longer before we take the break. So what we did so far was we used count vectorizer to kind of count words. So we did something like this. Oh, it's actually taking quite a couple of minutes to run. There we go. So we did something like this that basically says for each document, we're going to count how many times different words appear in it. And you can see that most of the time, so this is the first review. So yeah, most of the words appear 0 times, but I guess there's a word here that appears 12 times in that review. And so I can just talk a little bit about some of the hyperparameters here that we glossed over a couple months ago when we talked about this first. So we briefly mentioned, so min df is min document frequency. And that's to say that a word needs to appear at least 5 times to even be considered a word. And so when I add in this hyperparameter, instead of having our transform data be, so 37,000 is the number of reviews, 90,000 is the number of words, but if I require that a word appears at least 5 times, then I only get 32,000 words in my data set. And likewise, you can also have max df, which says, well, if a word appears more than 100 times, I'm not going to include it either. 100 is the maximum, and that's to take out words that are perhaps so common as to be interesting. So I can add that as well. And now I should get something smaller than 32,000 because I've added another restriction. Okay, so now I've brought it down to 27,000 words. By the way, why would you even want to do this? It relates to the feature selection kind of lecture screencast thing that I did. More features isn't always better because it can cause overfitting. And if you're pretty sure some of these features or columns are not useful, it's better to get rid of them because even if they're not useful, you can still overfit to them. And so, and then the other reason to do this would just be speed. Maybe your hyperparameter optimization is just too slow with 100,000 columns. And so you want to bring it down to say 1,000 columns just for that reason. So a couple of motivations for why you might want to do that. So here I'm telling it, you have to stick to 1,000 features. And so it's taking the 1,000 most popular words of the words that are allowed and throwing away everything else. Question in the chat, shouldn't we also be using stop words? Yeah, so there's another stop words argument, which will throw away words like the and, which are not generally useful. And so you can tell it to use the default set of stop words in the English language like this. And I think that's actually what I do in homework 6. Yeah, so that's another good one. I'll leave that in. Or you can just give it the words yourself. You could say, you know what, the only words I care about are good, bad, silly, and horrible. And then you're only going to get 4 columns. But now that, I mean, this might not be enough information because if you have a word like crappy or amazing, you're not going to be able to learn those words and how they affect sentiment because you've just restricted yourself to these 4 words. Let me just take a look in the chat. Are some languages way easier than others for a computer to understand? I really don't know. Yeah, I don't know. But I would expect that the technology, like the more research has been, a lot of research has been done on English. And so it might be more advanced only for that reason, but but not necessarily for any kind of fundamental reason related to the language. That's why AI can be dangerous. Yeah, and we'll be talking more about that. Fruit doesn't fly. Tell that to the tomato I used. Okay, thank you. I'd imagine Python is pretty easy for ML models to understand. Not sure exactly what is meant by that. Just curious, is complex words sentences easier for computers or simple words but repetitive sentences easier? I don't know of like a general rule on that. I guess, yeah, I don't know, but I'm guessing it kind of depends on what you're trying to accomplish and the details. I would expect there wouldn't be like a universal answer to that question. Okay. Let's. Will we take into account the order of the words too, as well as neighboring words? Yeah. So you can absolutely do that, and we will do that. But let's take our break now first, and then we'll come back at 11:41 and keep going with this. Okay. Yeah, so I just added in during the break. So the stop words we talked about, someone asked about multiple words. So there's also this n-gram range parameter or hyperparameter inside of count vectorizer that tells you, like, do you want sequences of words? So by default, it's 1, meaning just single words. But if you go from 1 to 2, that means include single words and pairs of words, or you could just do 2 or 1 to 3 or whatever. And so what you can see is if I go from 1 to 2, interestingly, it picked up on a working class as a common pair of words to include in this 1000. And if you look at overall all the different things it picked some of these years and stuff. But yeah, there's some like beautiful film and stuff that it picked up on, which are kind of useful to have in there, action-packed. Now, keep in mind, these are not feature importances. These are just things that Count Vectorizer picked as like common phrases to even have as features, which means like they kind of even have the option of being included, but maybe their feature importance will end up being close to 0 because they don't have any predictive power. And so in a way, there's kind of a two-step process for something to get included. Like Count Vectorizer has to even put it in there as a column in the first place to even be considered based on these hyperparameters. And then your model, like say if it's logistic regression, is going to try to fit and make use of all the features, but it could still, again, like assign a coefficient close to 0 for that feature potentially. Okay, so I want to briefly talk about TF-IDF. It's a popular thing, so I think it's good to know about. It's very, very similar to Count Vectorizer. It has a small difference that it normalizes the word count based on the frequency of the word in an entire data set. So the idea here is that if earth-shattering appears in a review 10 times, maybe that's more important than if movie appears in a review 10 times, because earth-shattering is not that common in the entire corpus, whereas movie is super popular and you're somehow less impressed to have it in there. And so you can import TF-IDF vectorizer the same way you would import count vectorizer. I'm not really going to go into the details of how it works, but the shape of everything is exactly the same. So you have kind of the same hyperparameters, and let's look at this kind of example case. So this is just a little. The word corpus just refers to like a data set, a text data set, basically. So we have 4 documents, which are kind of like our 4 movie reviews. And when we call count vectorizer on it, then this is what we get. So document 1 has the word document. First is 2 of the and one of this, so on and so forth. When we use TF-IDF vectorizer, then we get these kind of continuous numbers out of it, where the counts are normalized by how frequent things are. And so it looks at, I believe, the frequency of the word in general, but also the length of the document. So you'll see that these numbers are higher than this number, even though they all contain the word document once. And I believe it's because this first document is longer, it has more words in it overall, and so kind of relatively to it, this Word document kind of gets less weight. So I don't have a strong opinion on this. I guess I'll just have my same opinion I have over and over again, which is set up, unless you have some human intuition reason about why something would be good or bad, if you have a good validation procedure and you don't kind of overuse it too horribly, you could always just try this out and see which one works better for your problem. And I think it is probably safe to say you would not want to scale your features after doing this, because that might not nullify the whole thing, but part of the point of this is the scaling. Okay. Let's talk about word embedding. So now we're going to get to, so that was kind of just some language stuff that I thought was worth mentioning, but now we're getting back to the part where, I feel like there's this emerging storyline between the last 3 lectures, but I just haven't got it perfectly. Because, see, what happened 2 lectures ago at the images is we took an image and used that pre-trained model to transform an image into basically a vector. And then we did supervised learning on that vector. The truth is, once we turn the image into a vector, we can do all kinds of things on it. So one thing we didn't do is you could combine what we learned in lecture 13 with what we learned in lecture 14 last lecture. And if you wanted to find similar images to an image that you had, well, you could use that pre-trained model that I showed you. You could transform all your images, and then you could use nearest neighbors, which we talked about last time, to find similar images. And it would work a lot better if you use one of those pre-trained networks than if you yourself just tried to define a notion of distances between 2 images. If you just transformed all those images the way we talked about and then used Euclidean distance, it would work a lot better. And it's getting into this idea of embeddings. And so I suppose what we were already doing 2 lectures ago was we were embedding images into this vector space, into these vectors of a certain length. And we're going to do the same thing with text. And I should say, even count vectorizer or this TF-IDF vectorizer, they're kind of doing that too. They're taking a text and they're sticking it in some format, which is a bunch of numbers. In this case, 4 different numbers. And even last time when we were trying to compare different items, the way we were thinking of items is we were thinking of them as in this space of what did all the users rate all the items, and that allowed us to start comparing these items. And sometimes these spaces result in sparse vectors, like with the user thing, we had mostly zeros, and that's why we talked about sparse matrices, and same with count vectorizer. And sometimes they result in dense vectors or embeddings. And so I'm going to talk about word embeddings, meaning embeddings for language beyond count vectorizer. And I'm going to go back to what we talked about 2 lectures ago, and we're going to use a pre-trained deep learning model to do this. So here's kind of idealized version of what embeddings might do. If you were embedding into just a 2-dimensional space, meaning each word was just going to be given 2 coordinates, then maybe this would be like a good embedding. So you have like kind of bad things up here, good things down here, and these other types of words over here. And then if you're doing nearest neighbors, and you would say, what word is similar to nice? You would say fantastic is similar to nice, good is similar to nice. And And that would be kind of nice. So how can we get this kind of transformation? Well, you could, yeah. So here we can't use count vectorizer to do this because count vectorizer does something to documents based on words. But if we want to do this for words themselves, we don't actually have a way of doing this. Okay, so we talked about this. So here's how people approach this in language. So there's this ideas from not recent ideas. You shall know a word by the company it keeps, or if A and B have almost identical environments, we say that they are synonyms. So for example, her child loves to play in the playground and her kid loves to play in the playground. And so the strategy people are going to use for this word embedding thing is they're going to ingest giant amounts of data, like crawl the web for giant amounts of data. And they're going to say, well, here's a possible mapping for a word into a space like this. It won't really be two-dimensional. It might be like 100-dimensional, but here's a possible way of mapping a word into 100 numbers, which is the same thing as a 100-dimensional space. If I do it that way, then I would, like a good way of doing that will be such that child and kid are close to each other in distance, because from the massive amount of data we ingested, it seems like they kind of appear in similar contexts. So a simple approach to this is a co-occurrence matrix. And so what you can do here is, well, let me run the example and then I'll talk about it. So you have a bunch of different documents. And so now imagine the documents are like millions of web pages that you crawled off the internet. And you can say, for each word, what are the documents it appears in? And then similar words will be words that appear in similar documents. And maybe it won't be the whole document. Maybe it'll just be the neighboring words on either side or something like that. There's a bunch of ways you could approach this. And now you can say, let me map these words into a space such that two words are similar when they're kind of, their signature here is similar. So for example, data appears in documents 1, 4, and 5, and information appears in documents 1, 4, and 5. So I'm going to say they're similar, and I'm going to put them next to each other in this embedding. Notice how similar this is to what we're doing with users and items last time. And again, I feel like I'm just on the cusp of a breakthrough of tying this all together into a nice story, but I will get there eventually. I still feel like I'm not quite there. But it's very similar to what we were doing with where we had items over here and users over here. And we were saying, hey, for each item, what users rated you? And here we're saying for each word, what documents are you in? And then we were saying two items are similar if similar users rated them. And here we're saying two words are similar if they appear in the same documents. But what we weren't doing last time is this embedding thing. We weren't trying to map Amazon items into some kind of space like this. And that's the extra step we're doing today. We're saying, okay, we have this way of checking if two items are similar, so then let's put them next to each other if they're similar, or far from each other if they're not similar. Yeah, okay, so other ways you could do this is you could look at, you could make a table of words by the words themselves, and you could say the kind of vector of a word is all the other words that it appears together with, and you can again get something similar, and it's kind of the same sort of idea. Let me stop here and look in the chat. In this case, what would the two dimensions mean? Could we derive some kind of meaning through the coordinates of words or the distance of words from one another? Okay. Great question. So let me scroll back up here. Yeah, so when we do this kind of embedding thing, the goal is not necessarily to have any sort of meaning. And going back to the images from a week ago, we used that pre-trained network to map an image into a vector of, I don't remember how long it was, maybe like length 1,000. And then we just stick those vectors into logistic regression and got pretty good results. But we didn't really have meanings for those different features that we made. And so it's the same thing here. We're not necessarily looking for meaning to the features, but we're looking for a way to map words or documents into a vector so we can do stuff with them. With count vectorizer, they actually do have meanings, because the meanings of the different features are, well, how many times did this word appear? How many times did this word appear? But more generally, we're not having that as a requirement, and we're just looking for any way of mapping words or documents into, or pieces of music, like I was saying before, into a vector of a bunch of numbers. So, okay, there's a bunch of ways you could do this that are kind of similar to the user item stuff. I'm gonna rush through this a bit because there's more things I want to get to. A general distinction I want to make, which I talked about a bit before, is this idea of sparse versus dense vectors. And so, and again, with the user item thing last time, it was very sparse because a given item was only rated by a tiny, tiny fraction of users. So likewise here, a given word only appears in a small fraction of documents, or only appears in the presence of a small fraction of other words. And so a lot of approaches to this will end up with these very sparse vectors, and that's okay, but it's just good to be aware that that often happens. And then the kind of alternative is to try to learn shorter dense vectors. So by dense, I just mean not full of zeros, but with all kinds of numbers in it. And that's what we were doing with the images a week ago. And that's what I want to show you here and what you're going to look at in homework 6. And these are kind of favored, and they seem to be doing a good job recently. And again, we have pre-trained models that are going to do this. So we don't have to do all of this ourselves. Just like with the images, you can download a pre-trained model, and they're very useful. So I just want to show you, them in action. You may have heard of some of these things like in the news, like word2vec or something like that. So this is literally taking a word and converting it to a vector. That's why it's called word2vec. And so I'm not going to go into any of these and how they work, just like in the vision lecture, we didn't go into how we were converting those images into these vectors. But yeah, I don't think I even, well, sure. But they involve crawling giant amounts of text, for example, on Wikipedia. I guess that's what I want to say. So I'm going to show you some examples here of some really cool results here that are unexpectedly good. So this was kind of a big deal in the field or in the news. I don't remember exactly this was, but a while ago. So for example, if you could turn woman, king, and man into a vector, what you can do is you can try to do analogy. So you can say king minus man plus woman, and literally do the math on those vectors. So king is a 100-dimensional vector. You could subtract the vector for man, add the vector for woman, and you could then take the result and find the closest word to the result. So king minus man plus woman is going to give us some new vector that isn't exactly the vector of an English word, but we can find the closest English word to that vector. And so I'm going to show you that now. Yeah, okay, we kind of talked about this. So for this next part, if you're following along the lectures and running the notebook, this is a giant file that I'm downloading, which is the pre-trained word embedding. So again, this came from Google News. So there's these giant things where they scrape the internet and then pre-train the models based on this kind of idea that similar words appear in similar contexts, like we talked about. And then just like a week ago, we can download the pre-trained models and we can use it immediately. And so one thing we can do is we can calculate similarities, which is, it's giving us cosine similarities between the vectors. So for every word here, like pineapple, I can now turn it into a vector. And mango, I can turn it into a vector. And I can get the similarity between them. And you can see the results are actually making some sense. So these two fruits have a higher similarity, and sun and robot, which don't have that much to do with each other, have a lower similarity. And so what we can do is we can actually say, okay, find me the most similar word to a given word. It'll just search through all the words in its vocabulary and find me the most similar. And so the results are pretty cool because it takes a bit of time to run. So maybe I'll start these running and I'll look at the questions in the meantime. Okay, sounds like Yushi knows more about this than I do, so I'll stick with his answer to that question in the chat. Okay, so here's what it found as the most similar words to UBC. So this is very cool because these are, as you may know, universities, and no one told it about universities. It just noticed through massive amounts of data on the internet that UBC and UVic tended to appear in similar contexts, something much more sophisticated than that. And I mean, you could probably fill multiple lectures worth of going into the details of how it works. And it does involve some deep learning neural network stuff, as it did a week ago with images. The results are very impressive. So most similar to information, this is what it found. And the question in the chat says, how does it deal with words that didn't show up in the pre-trained model? So I don't think it can. And that was this cell that I skipped over here. So this pre-trained model is aware of 3 million words. So that's actually quite a lot of words that it's aware of. And so it has pretty good coverage, but you're right. If it's never seen a word before in all its crawling of the internet, then there's nothing you can really do. So yeah, you can find the odd one out. So you take all of these and say which one doesn't fit, and it says UBC is the odd one out here, which is really cool. You can also find the distances between sentences. So you have some sentences. Obama speaks to the media in Illinois. The president greets the press in Chicago. Notice how, okay, here's why this is more powerful than count vectorizer. With count vectorizer, it's just literally counting how many times a word appeared. But this is not showing words. This has Obama here and president there, Illinois here, Chicago there. But with the embeddings, they're getting embedded into a space, and Illinois and Chicago are going to be near each other. And so it's still going to know they're similar, which is why this is so powerful compared to just looking at something like word counts. And then here's this random thing about data science, and you'll see that the first two sentences have a lower distance. They're closer to each other than the two sentences that are unrelated to each other. So we can also do analogies like we talked about before. So man is to king as woman is to blank. And here are the top choices that it returns. I don't think you're going to find yourself in a situation where you need to do this for a project, but I just think this is such a cool illustration of how powerful these embeddings are, that it really does seem to be putting words similar to each other, kind of near each other. And it does seem to be understanding language to some extent. I think these are really cool results. So for the hockey fans out there, Montreal is to Canadians as Vancouver is to Canucks. Again, no one put this in here. This is just from crawling lots of stuff on Google News. Microsoft is to Windows as Apple is to Mac. And Gauss is to mathematician as Socrates is to philosopher. So one thing I want to talk about is implicit biases and stereotypes. So you may have seen this in the news, but because there was no human intervention in this, it just ingested whatever it found on the news, and that became what this neural network model believes. And that can be bad because we can't, it's just finding all the stuff out there, including with all the flaws of all the stuff out there. Not even to mention fake news. And I mean, these things are crawling news and all that kind of stuff. And so sometimes you get things that really give you pause. And so, for example, if you ask it for the analogy, man is to computer programmer as woman is to what, this is what it gives. And this is frustrating. This is what the model decided to predict based on the data that it was given. But if we just let these systems loose and this system is making decisions in some way, maybe not exactly by calling the analogy function, but if the embedded knowledge inside the system is used to make some kind of decisions that influence our lives, that could be really problematic. And you may have seen some of that in the news about resume screening and parole and all these kinds of things. And we will talk more about this on the ethics class later in the course. But there's like the cool part, and then you look a little deeper and you start to worry. And there's very similar things with images. So there was some results on images that I end up not showing a week ago that I'll show you at the end of the course, but it was doing similar things based on like the color of someone's skin. It was predicting something nonsensical for an image and stuff like that. So there is a lot to worry about. This paper here that you can click on the link is about de-biasing. So trying to take bias and stereotypes out of these models. And I think the more like modern, this is a little bit old, but the more modern word embeddings are a little bit better in this regard. I'm just looking in the chat. There's a lot of stuff. Guess I'll just stick with yeah, so I don't actually know how the de-biasing works, but maybe Yushi knows, or you can check out the paper. But it looks like Yushi has answered most of the questions in the chat, so I'm going to keep going in the interest of time. So here's something that I added for this year that I didn't have in the course before, which is a spaCy package. spaCy is a very user-friendly package to do all this stuff. So if you find yourself wanting to do NLP stuff, I think spaCy will be really nice to have in your toolbox. And so I have you use it a little bit in the home. My original motivation was that I had a lot of complaints last year about the code being too slow to run in homework 6. And so I switched it over to spaCy because the code was also a lot faster, because they had a much simpler model in there that was, anyways, that a smaller model that didn't involve as many words, and it didn't have as big of a download and didn't take the code as long to run. So I just want to show you spaCy. It's like very actively developed. There's this course by Ines Montani, who's one of the core developers of spaCy. That's like this nice interactive course. That's a good resource for you. We actually used her platform for a course that we made recently at UBC, or a series of courses. Anyway, so yeah, in the homework, there's some instructions for you to install spaCy. You all installed the course environment at the beginning of the course, but I hadn't anticipated using this because we didn't use it last time, so you'll have to install it yourself. But here I load these the pre-trained model, which includes the embeddings and whatever else it has in there. And they have pre-packaged within spaCy, like a small model, a medium, this MD is for medium, and a large one. So the large one is kind of massive, like the one I was using before, but I'm having used the medium. So it's not so big and slow. So you can do kind of the same stuff we just talked about before in spaCy. You can take the sentences, get the similarities, the similar sentences have a higher similarity score and all that. But these packages can actually do other things that that tend to come up very often in projects. So for example, that thing I told you about building a social network between companies by scraping public filings. Well, the first thing you have to do there is given a piece of text, you have to identify which words in there refer to companies. Like Greets is not a company, and we know that, and Chicago is not a company, even though it starts with a capital letter, and we know that. But Apple is a company, and Microsoft is a company, and Apple is a hard one because that's also a fruit, right? So that's called named entity recognition. It's you want to find named entities inside of text, and that would be the first step to finding relationships between companies. In the filing for Microsoft, you first need to find all the companies that are mentioned before you can even start inferring, is this a cooperative relationship or a competitive relationship? So spaCy, you can get the named entities using ents. So this sentence, this Obama sentence, it figured out that Illinois is a named entity. And so this is a bit different from the embeddings we were just talking about, but it's another NLP task that these packages can do for you that I thought you may find useful, and that's why I'm telling you about it. So it finds out that Chicago is the entity. I have no idea how this works or how much labeled data went into this to make this work. But the last one had no entities. And they just have really nice stuff in spaCy. Like they have this Jupyter thing where you can, it can label the sentences for you and say, this is an entity, and this is also the type of entity. They have different classifications of entity. I think GPE stands for geopolitical entity. So not only does it find the entity, but tells you what type of entity it is. So for example, for this movie review, from the movie review data set, if you run the spaCy code, it'll label it for you. And so it'll tell you all kinds of interesting things. Like you can see this is a date, this is a date, this is a geopolitical entity, Mickey is a person, Mickey Mouse is a person. So yeah, this is just really slick and really user-friendly and easy to use. So you may want to check out spaCy if you're working on something like this. Yeah, ordinal, all that kind of stuff. So I think the whole point of this is, and I maybe should have made this as an example, I feel like this should be able to tell that Apple is a company rather than just a fruit. But I guess we can try it out in real time. I'll probably regret this, but let's give it a try. Why not? Yeah, so it says Apple is an organization. I wonder if it works without the capital A. Just got super upset at me. Hey, I didn't do anything wrong. Oh, no entities found. Okay, I see. So it seems to be confused by the capital letter. Although, how about delicious fruit? So here I made it the capital letter because at the beginning of a sentence, but it still thinks it's Apple the company. So yeah, it's not perfect. But I also didn't download the fanciest one they have because I wanted to save space. So what can you do? Yeah, so this is just showing the same thing as that. Okay, any questions about spaCy? Okay, yeah, so let me try to wrap up my thoughts about what's actually going on here. Originally, I wanted to make this lecture about feature engineering. The thing about feature engineering is it is the most task-dependent part of machine learning. I mean, like the stuff I've taught you about cross-validation can be applied in all the different domains, or the stuff about splitting or overfitting or hyperparameter tuning. But now in the second part of the course, we're getting more and more domain specific. And so it's very hard to teach feature engineering. I mean, what feature engineering is coming up with good features that will be useful for whatever you're trying to do. And how you go about it depends on your data type and your problem. At least by showing you what I showed you in the last few days, I showed you a lot of pre-trained neural networky type feature engineering stuff, which is actually often very, very good these days. So back in the day, like say 15 years ago, if you wanted to predict something about an image, there were these engineered features. So for example, there was something called SIFT features that was actually developed at UBC, but the whole world used SIFT features. That was like the best thing. And it looked at the pixels of the image and came up with like important pieces of information and looked for kind of patterns in the images. And then you turned that into basically a bunch of numbers that represents an image, and then you could start predicting things. But how you would, that was like years of research that came into that. But if you're doing text, it would be completely different. And then if you're doing a different language in text, it'd be completely different again. So these deep learning things, they now seem to work better in a lot of domains than all that other stuff. Especially with like image, video, text, it's kind of dominated by these deep learning things. And for you, I think these pre-trained models will often be super useful as a way of getting features. Next class, we're going to talk about time series, and we'll talk about some feature engineering specific to time series. So if you have time, how do you engineer features out of time to be useful for prediction? But it's very hard to make general comments. So like, for example, in the house prices thing we talked about before, maybe we had a feature that was number of bathrooms, and maybe we had a feature that was number of bedrooms, and we could engineer a feature that was bathrooms per bedroom, and we could make a new column, bathrooms divided by bedroom. And maybe we would even delete the bathrooms in the bedroom column, or maybe we wouldn't. And it kind of depends on, so those types of things can still be useful. So for example, I mean, a really complicated model should be able to maybe learn that it needs to divide bathrooms by a bedroom, but it's not kind of natural for it to do that. And it might not even be possible like with a linear model. So for a simple model like a linear model, it is literally not capable of dividing two numbers and realizing that maybe bathrooms per bedroom is super important. And so you could help it not underfit, you could allow it to learn bathrooms per bedroom by putting that in explicitly as a column. For a complex model, it can learn whatever it wants, but maybe it's going to learn patterns that aren't even useful. But if you believe this to be useful, you can put it in and maybe you'll get a better score. So feature engineering is very important, but it's very problem specific. And so I guess I want you to be aware of this deep learning stuff for the particular domains where like a pre-trained deep learning model will give you useful features. And then other than that, I still need to think more about how to teach this. Maybe just giving more examples and doing feature engineering would be good. But that's kind of my general thoughts on feature engineering. And I hope that kind of answers the question of the person who mentioned this in the beginning. Even if you're still a bit disappointed, maybe this would be useful rationale. When I saw feature engineering on the course, I thought we'd be going to talk about how to pick, eliminate features, PCA and stuff. Okay, got it, I see. So about how to pick, eliminate features, that was the lecture 12 that we kind of skipped. And so I made a screencast for that, which you can watch. And I talk about how to eliminate features using the tools in scikit-learn. And then PCA and stuff is not covered in this course. It's covered in 340, simply due to time constraints of how much we can do. As an aside, quickdraw.withgoogle.com was really cool, especially because at the end it shows you why the model decided on what it did. Okay, yeah, I think I may have seen that before, but I'll check it out again after class. Are there any final questions before we wrap up? Are we done with nearest neighbor? Isn't it related to outliers? We are done with nearest neighbors. There's a lecture coming up on outliers. There is a relationship between them, but we won't particularly explore that in this course. So I guess the answer is yes. Could you run the sentence above while I was eating an apple with apple not capitalized? Sure. But hey, you can also run this. Yeah, so it is figured out in that case. Yeah, you have the notebooks, so you can run this, you can run all this code yourself too, and I, of course, encourage you to do that if you have time and interest. And it's not even a big download for this spaCy thing. It's like 50 megabytes for this medium model, they call it. Okay, I think we can wrap it up here. See you Thursday.